Well, I'll start. I mean, for a while, I haven't looked at El Nino research. Most of my research right now focuses on the interaction of climate and humans and terrestrial and marine ecology. But every once in a while, when we conduct a new computer simulation in our center, I'm tempted to check out what happens to ENSO in these model simulations. And in this particular case, we found something quite surprising and exciting enough for me to go back to this very old subject from 26 years ago. And I wanted to share with you some of the recent findings. And of course, this is happening in one or several models. Whether this is realistic is something we can discuss later on. Anyways, this is work done in collaboration with colleagues from the University of Hawaii and also from my center, the IBS Center for Climate Physics at Busan National University, and also Alfred Wegener Institute and the Irish Met Office. Okay, so I understand you're working in this large transregio on energy, and myself, I'm not working much on energy in atmospheric and oceanic systems, but I think maybe the closest subject in this direction is essentially to look at the variability in the climate system and how it actually may change with future climate change. So you're perhaps all very well aware that there are particular climate modes in the climate system, such as ENSO, of course, we'll talk about that one, the Southern Annular Mode, Pacific Decadal Oscillation, the Pacific North America pattern, the North Atlantic Meridional Mode, also called the Arctic Oscillation, or the Atlantic Multi-Decadal Oscillation, which Carsten almost alluded to, going back to some of the research that I did during my PhD, looking at multi-decadal variability in the Atlantic. So what is actually quite interesting, we treat these modes pretty much as independent modes. They're patterns. Maybe they are in some way coupled with each other, but usually we regard them as independent modes. And I will talk about a model solution today that in response to climate change shows that these modes more and more synchronize, and essentially El Nino becomes the main conductor of this kind of orchestra of climate modes. Let's take a little step back here. Let's just take a look at some of the raw time series from these climate modes to get a feeling for what this variability looks like. And of course, this is also related in some way to energy in the climate system. Up here, we have the North Atlantic Oscillation in the observations, and you can see the variability includes a lot of noise. There doesn't seem to be any particularly well-pronounced low-frequency variability in there. If we go to the North Pacific, the Pacific Decadal Oscillation, we see very different behavior. This is temperature here. The other one was sea level pressure difference. And there is much more low-frequency variability, maybe even some kind of pronounced variability on a timescale of decades or several decades. If we look at the North Atlantic, it's a very strange situation where we have essentially very low frequency variability. On top of this, however, there is also some higher frequency variability. This is clearly a very different characteristic from any of the other time series. And then we have ENSO characterized here by sea surface temperature anomalies in the eastern equatorial Pacific. And you can see the high frequency variability seems to be almost gone. And we have some much more low frequency-ish variability with timescales of several 2 to up to 10 years. And well, to characterize this variability, we can, of course, calculate the correlation function. The autocorrelation function where we have the time series and we shift the time series by a lag of tau and we divide by the variance. And then we have essentially a normalized index that tells us how much information is in the time series a little bit later, lag tau later. So this is, of course, a very meaningful variable because it tells us something about how long the memory in the system can be retrieved or maintained. And we can take the Fourier integral of this autocorrelation function that becomes essentially the spectrum, the power spectrum, if we square that quantity. And what we can see is this is very crude. Of course, you should not do a power spectrum fast Fourier transform of a stochastic time series, but here it's easy to see the key features. The NAO, North Atlantic Oscillation, is pretty much wide. We have variance on all timescales. The Pacific Decadal Oscillation, high frequency variability. So on the right, we have high frequencies. On the left, we have low frequencies, is suppressed. And we have this increasing slope here towards higher variability. And that is also referred to as red noise. If we look at the spectrum of the AMO, it looks a bit different. There seems to be also scaling behavior, but much more high frequency, low frequency variability here, perhaps also partly driven by external forces. So it doesn't mean that any of these time series is only internally generated. There could also be some components from the external forces included, such as volcanoes, aerosols, or even greenhouse gases. Then if we look at the ENSO time series, very clearly we see some interannual variability that seems to be very well pronounced. And keep in mind, these are logarithmic axes here. So actually, this is quite a substantial increase in the variance in the amplitude of variability on timescales of 2 to 10 years. Okay, so we can split up, if you like, the variability in our climate system as weather, maybe weather noise. We have climate noise, which is essentially the continuum that we saw in some of these time series earlier on. And then there are preferred timescales in the system, such as with ENSO, which we can refer to as climate modes. Okay, so all of this can be subject to changes in the climate system, such as external forcings, could be paleoclimate forcings, Milankovitch cycles, volcanic forcings, or even greenhouse gases. And so I wanted to go a little bit more into this idea of timescales and the coupling between different components in the climate system. And I'm going back here to Klaus Hasselmann's 1976 stochastic climate model, Ansatz. And the idea is that we can split up essentially climate and weather variables. The weather variables, they have an autocorrelation function that decays very quickly. So this is this red time series, the red autocorrelation indicated here. So we have a very small decorrelation timescale. And we can go back to the autocorrelation function of a typical climate mode, such as ENSO or the Pacific Decadal Oscillation. And we have a much longer timescale here of the decorrelation. And keep in mind that timescale here is defined as the decorrelation timescale. That's very important. And for the climate system, the inverse timescale is a damping scale, which has a physical meaning. We will come back to that later on. But the typical decorrelation timescales, if we look at physical processes, for instance, for the mixed layer in the subtropical regions, is in the range of a few months. If we look at the typical decorrelation timescale of, let's say, changes in the Atlantic meridional overturning circulation, it's something in the range of 10 to 50 years. Ice sheets could be much longer. So every physical system has a different timescale, damping timescale in the autocorrelation function, which we can relate also to the physical processes. Okay, so Hasselmann then went on to say, well, we have the weather, which we can define, which we can describe through symbolic differential equation, where the time derivative here is some kind of function of the weather itself and the climate state itself. Furthermore, this slow, more predictable climate state also has a time derivative, a different function which is also related to the weather itself, but also the climate state itself. And now here comes the main idea, and it's all very much simplified. If you really like the full picture, read the 1976 paper. It's really remarkable. It gives remarkable insights into what the climate system actually, how it works on a more mathematical level. So here the idea is essentially we can split this component, this nonlinear function of weather and climate. We can split this into a climatic state. For simplicity, I just linearize, but you don't have to do it. And we split out the weather variable as an independent additive term here. So this is essentially like a separation, if you like, a linearization in these two components, the climate and the weather. So now we know that the weather decays, the autocorrelation function decays very quickly. So this is almost like a delta function. And the beauty here is if we have a delta function, we can describe the weather variable as stochastic white noise, because here white noise is characterized by an autocorrelation function that that has the shape of a delta function. Well, that gives us a simple version of the Hasselmann climate model where we have the derivative of climate, whatever temperature, for instance, is some kind of damping with respect to this variable, and some external forcing, which is driven by the weather processes themselves that are characterized by short decorrelation times. Okay, so then this equation, we can just apply a Fourier ansatz and say, well, the temporal variability we can write essentially as a Fourier integral. Here we can plug this in. This one gets an I omega t, the temporal derivative gives an I omega. The A moves over here. We can get rid of this Fourier integral later on. This one becomes the Fourier amplitude, and the Fourier integral of the white noise itself is as we saw for the North Atlantic Oscillation, for instance, is pretty much a constant amplitude for the Fourier component here. And then we can calculate the complex conjugate of this one, multiply these two equations. Here we get f squared. Here we get essentially C omega complex conjugate. That's the power. And then we have omega squared plus a squared. And voila, there is Hasselmann's Ornstein-Uhlenbeck process spectrum for the climate system. And the idea here is, well, already Einstein came up with a similar approach where he tried to explain Brownian motion. We have, let's say, big particles like milk molecules in a fluid, and they're just under the microscope, you see them moving around. But they're essentially kicked by many small molecules from the fluid who have thermal vibrations, and they kick these bigger molecules, and you can see in the microscope the big molecules moving seemingly randomly. So the big molecules is like the climate system, and the small molecules kicking around is essentially like the fast decorrelation weather. And this is quite nice and explains quite a bit of the variability on our planet. So it was called the stochastic climate model, or I prefer to call this a stochastic climate continuum hypothesis. And of course, it has its validity, but many parts of the climate system behave differently, such as ENSO. So if we look at the spectrum, for instance, of typical variables such as specific decadal oscillation or so, there are some features that really match this kind of continuum hypothesis. Okay, so climate is always variable, was the essence, and it's kicked around by the random weather noise. And this is a very influential paper, which was also mentioned in the nomination of Klaus Hasselmann for the 2021 Nobel Prize in Physics, which he shared with Suki Manabe and another physicist. Okay, so here is kind of the idea. You can see the PDO, this part omega to the -2 squared. That is essentially the structure of a typical power spectrum a la Hasselmann or a la Einstein or a la Ornstein-Uhlenbeck, who were the first to describe these equations. Now, what's the physics here? There is a physics. A contains physics. That's the decorrelation. Has something to do with a decorrelation or inverse decorrelation timescale. And sigma is the amplitude of the noise. So now there is an interesting part. You can fit, for instance, for the Pacific decadal oscillation, you can fit a typical spectrum a la Hasselmann, and you get a time scale here of about, I don't know, 100 to 200 months. But the question is, what kind of physics does this correspond to? And this is, I think, the really interesting question, to link these statistical timescales essentially with the physics. And this is where really the science starts. But this is a very simplified model. We can use more complicated models. For instance, we can argue that the noise in the atmosphere is not just white. It could be red. So we have another red forcing, another Ornstein-Uhlenbeck process where the atmosphere also integrates stuff. That makes sense because also the atmosphere integrates some of the low frequency variability of the ocean SST. So there is also essentially a low frequency enhancement over some areas in our atmosphere. And in that case, you will get a different spectrum, slightly different character and so on. Another possibility is to look at a more general model rather than using just a linear feedback here, as in this particular version of Hasselmann's model, which is actually by Claude Franquinol. We can assume a nonlinear function here, f of c. Again, some white noise some weather forcing, but the weather forcing itself can also be a complicated function of the climate system itself, and so on. And then we start to essentially couple different components in the model, slow components and fast components, and we can get much more rich variability, not just this continuum, but we can also get preferred timescales. So this is just a little overview of the generation mechanisms of variability in our climate system, and I will get back to some of this later on. Now, we saw the power spectrum of Niño 3, 4, 4, which is this eastern central box characterizing the amplitude of SSD variability there. And yeah, there was clearly a timescale. So how can we generate a timescale with the model of this kind of conceptual framework? And Carsten mentioned the hammock. Well, there, the idea is that, let's say, if you have a number of different variables, such as temperature in the eastern equatorial Pacific, maybe ocean currents or the thermocline depth in the equatorial Pacific, then you can find not only just one variable here, but essentially an entire matrix that links the current state to its future tendency, and also across these different variables, such as temperature, thermocline depth, and so on, you can have stochastic forcing and of different amplitude in these terms. So essentially, you're ending up again with something like a stochastic climate model, but now it's a multidimensional one, and that one can give rise also to internal frequencies, internal oscillations. So we need to go to more variables that are intrinsically coupled with each other in order to generate an oscillation. That's quite clear. In order to describe an oscillation, you need two ordinary differential equations at least, or at least one or complex variables. Okay, now we talk about these climate modes, but it's good to remind ourselves actually what a climate mode is, and there are different ways of characterizing this. Typically, we conduct some kind of statistical analysis, EOF analysis, or POP analysis, which some people call also linear inverse models. We apply this to the existing data and look for covariant structures and so on and so forth. However, there is a different way. If we had a set of equations, and these equations could be the full complex Navier-Stokes equations, or it could be a simple version, maybe even also empirically derived version, where we have a set of climatic variables as well as the tendencies, which are linked through a nonlinear function fi. Well, then the first step we should do is we should look at the stationary solutions where we set this to 0. We call that xis. And then every variable itself we can write down as a perturbation around the stationary solution. And that perturbation we then refer to as xi prime. Okay, so then from there we can linearize this equation. We can just plug this in. We know xis dot is going to be 0, and we linearize, and then the coefficients of this first linear term in the Taylor expansion are essentially the Jacobian, the entries of the Jacobian matrix. And that's quite nice because that again looks a bit like the stochastic climate model here without the forcing explicitly. But in any case, we get again this structure where the different climatic components are coupled with each other through these terms in the matrix. And that matrix is a Jacobian matrix. And we can plug in essentially an eigenvalue approach where we say, well, our initial perturbation, we are interested in how quickly it decays or whether it oscillates away and so on. And we just use this approach where we have an initial condition and some decaying, or lambda could be complex oscillating system. We can plug this in and then just get a linear equation for the eigenvalues. So that's normal eigenvalue equation, algebraic equation. So essentially going from a complex differential equation system, we can look at the stability of the system, the eigenmode stability through this lens of linear algebra. And that's quite nice and elegant. So now where are the eigenmodes? The eigenmodes are, or the climate modes are the eigenmodes of the Jacobian matrix. And this is actually a very powerful tool. So now the big question is, how can we efficiently obtain equations that describe the variability of the climate system in a meaningful way? Doing this approach for, let's say, a fully coupled general circulation model is almost impossible, even though for the ocean, people have tried to do that. But fully coupled is still a big challenge. Now, in order to do that, we later on will get back to more simplified models. Okay, so that brings me to ENSO. So we talked about variability, we talked about preferred timescales, and of course, ENSO is one of the climate modes that has this preferred timescale range, interannual variability. How does ENSO work? And that gives us an idea on how we can build a conceptual model. So now here, under normal conditions, we have strong equatorial trade winds blowing from east to west. So here we have Ekman divergence, so cold water is being brought up well to the surface. And we have a cold tongue in the eastern equatorial Pacific under normal conditions, whereas in the west, we pile up warm waters. That's where we have the warm pool, and there are also thermodynamic feedbacks that intensify that system. Okay, so if we have, I should mention we have this warm water sphere and the cold water sphere, and they are separated by the thermocline. Okay, now if the winds weaken, that happens every once in a while. We are looking at the wind anomaly now on the equator. What happens is that this warm water essentially sloshes over to the east as a Kelvin wave, equatorial Kelvin wave, and what it does, it warms the eastern equatorial Pacific. Why? Well, we'll discuss this in a second, but also there is positive feedback. If we warm this area, also this large-scale Walker circulation weakens, which further intensifies the westerly wind anomaly. Okay, so let's get a little bit an idea. Oh, the thermocline, the slope is now opposite. Previously, it was like this. Now it's opposite. Why? Because the anomalous trade winds, so here positive anomalies, they create a pressure. They have to be balanced with a pressure gradient, and that is the H prime dx, the H prime being the thermocline depth. So the thermocline tilt has shifted from this way to the other way. Okay, and then it's quite clear that also depending on, well, let's move on. And then what we have also, we have with this one reduced Ekman divergence, so less cold water is being brought up to the surface, but also the mean upwelling that we still have is pumping up, is bringing up much warmer water than under normal conditions where the thermocline is shallow and where we have colder waters closer to the surface. So essentially, if we look at the tendency equation for temperature here, we have, let's say, normal damping. If there is no upwelling change, we have essentially going back to climatology. And then, so this equation goes for the anomalies. And then we know that the amount, the temperature gradient itself is of water that's being mixed into the mixed layer is determined by the thermocline depth in the east, and that's HE. Okay, that's a simple model, but that's not the whole story because El Nino also disappears eventually. The seasonal cycle playing a role, but there is one other process. So if we think about this westerly wind anomaly that pushes the water over to the eastern equatorial Pacific through a Kelvin wave, what it also does is it actually is very strong on the equator because actually in the atmosphere it's also a Kelvin wave, but also the equator is a little bit weaker. So we create a wind stress curl, and this wind stress curl is directed in such a way, so it's essentially directed in such a way that we push water away, this warm water away from the equator, so we discharge the heat on the equator. And this is called the essentially discharge, recharge process. For a La Nina event, it's the opposite. We have the reverse trade wind, wind stress curl that pumps in heat from the off-equatorial regions into the equatorial region. Okay, that's a process that actually is generated by Rossby wave and Rossby wave reflection here at the western boundary, but the details don't matter for this simple model. So once the heat is drained because of this discharge, then essentially El Niño starts to die. Less warm water is here, so more cold water can be brought back to the surface, and we can generate a phase transition. And if we look at the typical El Niño time series here in red, sea surface temperatures, and then the warm water volume the one in blue, and warm water volume in red, we can see there is this almost 90 degree out of phase relationship. Look at this event. So as we are charging, if we are increasing the warm water volume, we are making the zonal mean thermocline depth deeper. Also El Niño develops, but as El Niño really develops, at some point, the discharge process becomes strong enough and the heat stored in the equatorial Pacific zonal mean is then starting to drain out, and that drain out essentially kicks in the phase transition into a La Nina event. It's not the whole story, of course, but it's a pretty powerful method. So let me summarize here. For the atmosphere, if we have warm water here, so sea surface temperature high, we have an atmospheric Kelvin wave response, and that Kelvin wave response creates a wind stress on the equator positive anomaly. So warm eastern equatorial Pacific, positive wind stress on the equator. Okay. Then what we also have is that if we have this positive wind stress, the thermocline will deepen in the eastern equatorial Pacific and shoal anomalously in the western equatorial Pacific, and that is done by an oceanic Kelvin wave and eventually Rossby waves on these sides. Okay, then we also have mixed layer dynamics and the vertical advection. We already saw the equation. The anomalous temperature tendency in the east is some kind of damping feedback. Think about the old Hasselmann model. And then we have the real dynamical feedback. The deeper the thermocline, the more warm water there is in the eastern equatorial Pacific, warmer water is being mixed to the surface, and that increases the temperature. So here we have a positive and then this is the spherotrope transport discharge. The warm water volume, or even Western Pacific warm water volume, again, we have some kind of damping here, going back to climatological state. But if we have positive wind stress, as we have for an El Niño, then this is a negative term. So this is discharging the heat away, and this is done by oceanic Rossby waves and partly also by advection. Okay, so this is a simple model. We can summarize this. So two ordinary differential equations, and these ones are diagnostic. We can plug them in, and we get something called the recharge oscillator model by Fei-Fei-Jin. And that one captures
Axel,
the acid. Yeah.
so can I ask a question? Because I was always wondering with this ENSO on the previous slide, waves, they do not advect anything, right? They don't advect the heat.
Yeah.
But in the second step, you said that there's this warm blob from the east is transported to the west by the Kelvin wave.
Yeah, that's not that's a colloquial expression. There are two effects. There is just a wave itself that does not transport any water, but we also have the zonal advection that is generated by the wind stress on the equator. So two components together.
But what is important or more important?
I'm sorry?
Which one is more important?
Initially, well, it actually depends a little bit. Some El Niño events, you see the zonal advection being more important in the beginning, and they can form these Central Pacific El Niño events. And some El Niño events, the Kelvin wave plays an important role, and that, of course, moves over to the Eastern Equatorial Pacific, and that can precondition the Eastern Pacific El Niño events.
Okay. And for the last step, there's also waves, right? Waves with this advection.
Yeah.
So what's
you have the wind stress curl generates Rossby waves. They propagate westward. I mean, you can see that here. This one propagates westward. And here, as they hit the coastline, whatever, Philippines and Papua New Guinea and so on. So there, new ocean currents can also emerge, and you have the reflection itself. So as you pile up the Rossby waves, you will also generate anomalous advection that partly discharges some of the heat, essentially also in the Western Pacific during that time period. And then these Rossby waves, as they become shorter and shorter, eventually reflect back into a Kelvin wave, and that's going to be an upwelling Kelvin wave that kills the El Nino in the east.
But then there's no role for advection in this picture.
Oh, there is a role for advection as these Rossby waves start to encounter the coastline, western coastline. They become shorter, and during that process, there is also some heat advection that is being taken out on the western side.
Okay.
Yeah.
Thank you.
Ooh. Yeah, sure.
Sorry, can I also ask a question?
Please, yeah.
Also to the previous slide. So you said these damping terms. So are they just brought in due to statistical reasons to kind of have this climate Hasselmann model, or do they also have a physical interpretation?
Yeah, they have a physical interpretation. For instance, if you say, well, we don't have any, let's say we have a temperature anomaly, but no thermocline anomaly here. So how long does it take for a temperature anomaly to go back to normal? That is determined by the air-sea interactions. And in the Eastern Equatorial Pacific, the air-sea interactions are negative, where essentially heat, you have evaporative loss, evaporative cooling, and you also have more clouds if you have a positive temperature, and more clouds, in particular more stratus clouds in that region, means there is less shortwave radiation, and that's also a negative term. So this lambda itself encapsulates evaporative cooling as well as the cloud radiative feedbacks. Yeah.
Okay. Yeah. Thank you.
Mm-hmm. Okay, so this is one simple way you can make it a bit more sophisticated. Here we have essentially, well, the Hasselmann model with interesting parameters, the amplitude of the noise, the damping, but all of these parameters, and here's a model that generates oscillations similar to what we see for El Nino. But all of these parameters can change due to global warming, orbital forcing, or any other processes, background state changes. So you have changes in the amplitude could occur if you change these parameters, frequency, the decorrelation time. If we include nonlinearities, we could have changes in skewness. The memory, of course, has something to do with decorrelation, and also predictability. So let's go back to a more mundane or realistic situation here. If these things can change, if these things might even change the amplitude of ENSO, do we actually see anything in the observations in the paleoclimate reconstructions? And that's a bit tricky. I don't want to go to all the details how you reconstruct El Nino with sediment cores, marine sediment cores, lacustrine, tree rings, annual corals, and so on. But if you put all of this together, all of them annually resolved, in that case, you can see that, well, there are two statements here. One is Kim Cobb wrote in her science paper, the 20th century ENSO variance is significantly higher than average fossil coral variance, essentially in the Holocene, which is interesting. So does it tell us anything? I'm not sure. So we did a reconstruction in 2013 also, where we focused a bit more on hydroclimate proxies. And again, there is some indication that ENSO is stronger, has been stronger at least in the last 30 years than before, going back 500 years. Does it mean anything? Is it clear evidence that El Nino is being changed already by global warming? No, definitely not. So, but that's something we're going to look at into now. But keep in mind, El Nino is changing, is always changing, but it has changed in an unprecedented way for the last few hundred years. Okay, so now Carsten introduced this old study from 1999 already, where Andreas Bacher ran the ECAM for OPIC climate model on the Cray C90 computer of the German Climate Computing Center in 1998, 1997. It was the longest computer model simulation on this computer at that time. And what we found was kind of surprising that El Nino in the model was very realistically represented, except the frequency. The amplitude of El Nino increased. And that is nicely illustrated here, where we look at the variance of ENSO as a function of time in this model simulation. Just look at the black line. This is now increasing CO2 gradually. And this was some kind of A1B scenario, I think. And what you can see is that here there's a big jump in ENSO variance and another jump in ENSO variance. And that was very puzzling. And in particular, here it's pretty abrupt, and it stays on that regime. If we compare it with a control run in green, you can't see that change. What you can see is this huge decadal ENSO amplitude modulation, which is also puzzling. But anyways, there is another one. So 26 years ago, there was some kind of evidence that ENSO could even rapidly change, at least in a climate model, whether in reality, we don't know. Okay, let's take a closer look. And the idea here was, because it was so rapid, that actually there is a kind of bifurcation in the system, that parameter changes or climate background state changes shift the ENSO system, that it undergoes a Hopf bifurcation. So what's a Hopf bifurcation? Think about this recharge oscillator model that we had earlier on. If we include a nonlinear term here, we can generate a Hopf. Well, we can have a Hopf bifurcation in limit cycles. So what is a Hopf bifurcation? Hopf bifurcation is if we have a complex eigenvalue in the linearized system in the Jacobian, then the system can oscillate. And on one side of this Hopf bifurcation, the oscillation is damped. But as we move to the other side of the oscillation, if we start with an initial perturbation, it will grow. So we have an unstable oscillation, but it cannot grow until infinity, because in reality, in our model, we have damping nonlinearities, and we end up with a situation where the system runs a limit cycle, a very regular high amplitude variability. That would be a very clear indication of this Hopf bifurcation. And what we would also see is a change in the amplitude, because here the system is damped. Still, noise can kick off El Nino events, but here on the other side, El Nino events would be self-sustained. So I try to figure out if this model behavior in this complex climate model at that time, 26 years ago, has anything to do with Hopf bifurcation. And there was some indication, so you can fit essentially an ordinary differential equation through some of the dynamical variables and then determine the eigenvalues of the system. And there, yes, indeed, the eigenvalue ran from negative, so damped oscillation, to positive, which is an unstable oscillation, which essentially saturates into a limit cycle. Okay, so now this is 26 years ago. And then now we are 2025. So we ran other climate models in the meanwhile. And recently we conducted a model simulation with the AVI climate model, Alfred Wegener Institute, CM3, in various resolutions. And the motivation had nothing to do with El Nino. As I said, I'm not very much interested in El Nino anymore, but it had other purposes. But this model simulation was conducted to get a better understanding of how climate change looks like on regional timescales. Okay, so the typical IPCC or CMAP type model simulation has resolutions of 100 to, I don't know, a few hundred kilometers. Then we have the high resolution model intercomparison simulation somewhere between 30 and 100 kilometers. We wanted to go down to 9 and 4 kilometers with our model simulation. In order to do that, we ran a particular protocol where we first ran the climate model at medium resolution, 30 kilometers, and then branched off with the same ocean resolution, but higher atmospheric resolution to run model simulations at 9 and 4 kilometers. Okay, so keep in mind, this is fully coupled, global, and we're using our own supercomputer, Aleph, for that we purchased here from our center in 2018. Okay, so that motivation was essentially to go from something where you can barely see, let's say, even the Korean Peninsula where I work. This is a typical IPCC model to something where we can have much more regional details. And this is, by the way, the warming signal for, this is a warming signal for one of the simulations. Okay, I'm sorry, it's not a warming signal, it's a mean anomaly, spatial mean anomaly. Okay, so that was kind of the motivation. The model, as I said, includes the OpenIFS atmosphere model, very nice, derived from the ECMWF atmospheric model mother, so to say. It is coupled with the OASIS coupler to the RV FESOM ocean model and the FESOM sea ice model. And the atmospheric resolution is shown here, 30 kilometer on the equator and something like 40 kilometer in higher latitudes. The 137 levels in the atmosphere and 80 levels in the ocean, but with varying ocean resolution going from 4 kilometer in the Arctic to about 25, 30 kilometers in the extratropical regions to account for the different Rossby radius of deformation. Okay, so now how good is this model when it comes to ENSO? Well, quite remarkable, actually. If we look at the sea surface temperature variability in the observations or reanalysis ERA 5, this is the typical pattern. This would be the pattern from the RV climate model. And we see, I mean, all of these patches come out really, really nicely, even the detailed structures here in the Malvinas and so on and so forth. Now, ENSO itself is seasonally modulated. So if we calculate the standard deviation as a function of month, in the observations, we get this gray bar histogram. And if we look at the climate model, RV, we get very similar amplitude and a very similar amplitude modulation. Then the spectrum there almost is indistinguishable, surprisingly, the observed spectrum and the modeled spectrum. And keep in mind, this is a fully coupled model. The model does not know anything about the observed ENSO, the real ENSO system. Okay, so and the model was not tuned for ENSO either, so this is a good thing. If we look at the Taylor connections under present day conditions in terms of precipitation patterns here in brown and green and temperature patterns and so on, you can see observations again or reanalysis and the model. And you can go into regional details and it matches quite well, but there are some discrepancies, of course. After all, it's a model. So among all the climate models I've seen so far, this is maybe the most realistic one when it comes to resolving ENSO amplitude spectrum, the phase locking with the seasonal cycle, Taylor connections, and so on. And here are some more regional features, the rainfall pattern during an El Niño event in the observations on the left, in the model on the right. And again, the match is quite remarkable. And this is a rainfall product. It's not it's not a reanalysis, it's direct observations extrapolated. Well, we're going to talk.
Can I ask a question? The usual problem in these coupled models is the double ITCZ right over in the ENSO region, right? Does it also have this problem?
Yeah, that model still has the cold tongue bias and the double ITCZ around it, but is not as bad as in the lower resolution versions and other models.
And you expect that this bias in the mean doesn't affect the ENSOs? So surprising, huh?
Yeah, in that particular case, not. We have seen other models where the bias is worse and where also ENSO looks less realistic.
Okay.
So, yeah.
Is there still room for improvement then?
I think so. In particular, well, the Taylor connections will be influenced by the biases, but also it doesn't seem to be that much of a problem here right now. I think, well, there are other horrendous biases, of course, in the North Atlantic and so on. So sure, we need to get rid of these biases. But in this particular situation, the ENSO variability comes out even with this bias in the background state still present.
Okay, thank you.
Weaker than in typical models. Can you just give me 10 seconds? I'm going to turn on the heating here. It's getting freezing cold in the conference room. 1 second, please.
Okay.
Okay. Right. And we're also going to talk about the North Atlantic Oscillation, and we wanted to just know how realistic is the model in representing the typical teleconnections. And here is on the left, again, era 5, regression pattern on the NAO. The typical thing, more rainfall in Scandinavia, less in the Mediterranean, and the model reproduces even the regional features quite nicely. Well, we know during positive NAO phases, you shouldn't go to Ireland sorry, you shouldn't go to Scotland to make vacation, summer vacation, or winter vacation even. So this is, by the way, winter here. And then this is wind speed, important for wind generation. Sorry, wind speed is here. This is then the temperature response. Okay, again, looks quite reasonable. Some features are not that well resolved. The elongated high wind speed anomalies towards northern Russia are not well captured, but otherwise it looks okay. Well, now coming to the model simulation, originally the plan was just to do this medium resolution simulation to spin off some higher resolution model runs 9 kilometer, and now we're doing 4 kilometer. But it turned out this medium resolution, 30 kilometer in the atmosphere, 4 to 25, had some interesting features that I will discuss with you. So regarding the pattern of climate change, so again, the forcing that we applied is SSP 5.8.5. I hope, of course, humanity can avoid this worst case scenario because that in this model would create another 7-degree warming over the next 80 years or so. So that would be horrible. So the model itself has a pretty high climate sensitivity. Now, here's a warming pattern on top of the background state and contours. The warming pattern enhanced warming in the eastern equatorial Pacific and in the cold tongue. So the cold tongue is warming faster than the warm pool, not unusual. And then we have a positive wind stress anomaly. Of course, clear, we have more warming here. We have a positive wind stress. And then also the thermocline is going to be shallower in this region as compared to the east because of this positive wind stress and the pressure gradient shifting. Okay, so that's kind of not an unusual pattern for climate change in climate models, but what it does to ENSO is quite remarkable. So let's focus first of all on the change in the standard deviation of temperatures. And this is the period, the last 20 years minus kind of the first 20-year period, or 30 years actually. So global warming minus current situation. And you can see there is a huge intensification of the ENSO variability, but overall SST variability increases almost everywhere in this model, which is remarkable. But in particular, the ENSO variability under present-day conditions we saw is very realistic, nice variability and periodicity. But then around 2060, the amplitude becomes stronger. And by 2080, the model is completely locked into regular, almost limit cycle-like behavior, which I've never seen in any climate model before, that essentially El Nino becomes a totally predictable cycle with 3 to 4 year frequency. So this, keep in mind, this is not a toy model. This is one of the most sophisticated climate models available that shows this behavior from stochastic, more stochastically generated ENSO to something that really looks like a self-sustained limit cycle. Now, interestingly, EC Earth does the same thing, apparently. So also looks beautiful ENSO-wise. And then also around 2040, 50, that model also generates this completely periodic ENSO mode, 3 to 4 year timescale, maybe 1 year, sometimes it's missed. And keep in mind, EC Earth, of course, also uses OpenIFS, the same atmosphere. I'm not sure if that plays a role, but this is not just one model showing this behavior. Now, we can quantify the regularity with some entropy measures. And yes, with this warming, we get an increase in the regularity, an increase in the amplitude, and this is the control amplitude. So we are diverging really far away from the normal that this model generates. It's an unusual behavior. And now we're coming back to these simple models that I introduced earlier on, just to get a little bit of an understanding what's actually happening here. And here we are referring back to this recharge oscillator model for ENSO. In a simple way, we can do it more complicated, where we focus on the Eastern Equatorial Pacific temperature anomaly and the thermocline anomaly averaged across the equator. And we can write the tendency as the matrix. Keep in mind, that's kind of the linearized Jacobian, if you want, times this vector plus some noise amplitude in both ENSO, maybe thermocline a little bit. Okay, so we can split up this ENSO term into essentially Biatness instability term. There is something that later on becomes a frequency, and there is another damping term here, the thermocline damping term. So these terms have physical meaning, as we discussed in the recharge oscillator model equation before. And from that, we can calculate the instability index or the growth rate of this equation. Plugging this in, we get essentially the instability has this imaginary part, which is a frequency, and then it has the real part, which is the growth rate. And we can estimate these numbers essentially from the data. We have the data from the climate model, we plug them in. In order to do it correctly, we also need to account for the seasonal cycle. So we're not just doing an instability analysis on a fixed background state, but a Floquet analysis. We can do it more complicated. We can say, well, El Nino itself does not live by itself, by its own, but it is interacting with the Indian Ocean Dipole, with the Atlantic, and so on and so forth. There are tons of papers about how other climate modes influence ENSO and the other way around. You can account for this in a more complicated, more six-dimensional world, and these parameters can all be estimated easily from the climate model in different chunks. So we can run it under present-day conditions. We can take a window and move that window over the time series and see how these components, how these numbers change and what it does. Okay, here we are again looking at the standard deviation change of ENSO, the amplitude. We looked at that before. Increases in ENSO amplitude, mostly in December, in the winter time, makes sense. Okay. Here is the instability, the ENSO growth, and we can see it increases actually quite early, but then it saturates. And this is the two-dimensional model. This is six-dimensional dynamical fit or empirical model, and so on. But what's also astonishing is that the noise itself intensifies dramatically. Noise amplitude is shown here in this red color. So you go from 2030 blue to 2090, and you can see the noise amplitude that drives ENSO is intensifying together with this instability. For the instability of ENSO, we can further figure out that's a different type of analysis, what is actually happening. But to keep it short, here we have a reduced damping from the thermocline adjustment. So thermocline adjustment itself is a negative feedback. Reduced negative feedback makes it stronger. And this is this minus epsilon term here in this equation. And then we have the Biatness feedback, the instability coming from the thermocline feedback itself. And that one is also increasing. And we can split it up. Is it which term it is? But that's maybe too much information here. The main question, the main concept here is the thermocline damping efficiency weakens. And why is that? It is because for the same El Nino, and this is the regression of the wind stress anomalies onto the Niño-3 in a window, what we see is that essentially the wind patch that is created during an El Nino event now and into the future gets broader, which means with every El Nino, we are also starting to generate more higher latitude Rossby waves that contribute to essentially the discharge. But the longer and higher meridional number Rossby waves, they are less effective in the reflection, and that leads to a less efficient ENSO discharge. And if you're interested in the details, it's described and derived in the paper as well. So now let's talk about the whiplash effects. So looking at this El Nino variability getting very irregular, if we take the typical NAO time series, pretty much random before, but now with this very strong El Nino, what happens is that whenever we have a La Nina event, we generate a positive NAO in the right season. Or if we have a longer lasting La Nina event, that every winter season we will have a positive NAO. So you can see the NAO starts to become like the combination mode. It's essentially the product between El Nino and the seasonal cycle. And if you plot this product between the two, it almost looks exactly like the NAO. So with this one becoming stronger and more predictable, also the NAO will become, and winter climate over Europe will become much more predictable and stronger. So that's something to keep in mind, that currently NAO is maybe not a main driver. Sorry, ENSO is not a main driver for the NAO, but in future that might change if that model is correct. Looking at the typical Taylor connection from an El Nino under wintertime conditions under present day, well, there is not much going on in Europe. Rainfall anomalies, Klaus Friedrich documented, they are statistically significant, but they are just weak. However, in future, the entire ENSO-Taylor connection pattern changes completely and becomes the NAO over Europe and the associated, so there's negative NAO for El Nino, and the associated more rainfall in the Mediterranean and less here, and flipped around for La Nina. Okay, I will probably skip this, but just show that we can look at other climate modes as well, such as the tropical North Atlantic variability, the Indian Ocean basin mode, Indian Ocean dipole. These are all these modes that climate statisticians like, and all of them essentially become stronger, and all of them get more and more synchronized with El Nino. And I won't go into the mathematics of how to quantify synchronization, but it happens that all these model modes that are usually independent of ENSO become completely absorbed and driven and synchronized by El Nino, and become stronger and become more predictable. So this is kind of and the associated climatic impacts also become more dramatic. So this is one particular model simulation, but also the EC Earth seems to have a similar behavior. In future, according to these simulations, the winter NAO will be strongly dominated by ENSO, and also interannual rainfall anomalies across the world will have much more of this ENSO frequency, nicely predictable because very high signal to noise ratio, but also the amplitude will be larger with larger climate whiplash effects on the climate system. Okay, so I'll stop here and I'm happy to take any questions.